Okay, now we're going to talk about traveling sinusoidal waves and how can we create traveling sinusoidal waves. As you can see here, we have a source that is touching one end of a string and it's moving up and down periodically and performing simple harmonic motion. So uh, basically the motion of this source, that is up and down motion, is simple harmonic motion, and as a result the elements of the uh, string, if I take any point here, for example this point P, I find that it's going to move up and down in order to perform the propagation of this wave. So the wave that we obtain is basically a sinusoidal wave, and as with the pulses that we have talked about before, we can characterize this wave by looking at its propagation velocity and also look at its amplitude of the oscillations. Now we have a few things that we would like to define for this wave. First of all points like P that are the maximum points here are going to be called crests, and all the minimum points, let's call these points Y, and let's call these points P. All the minimum points, lowest points, will be called troughs. And if you look at the distance between two consecutive crests or two consecutive troughs, you will find that it is equal to one wavelength. So we call this wavelength lambda. So let's think about what types of motion are involved in the propagation of this wave. We have the two types of motion involved. So first of all, we see the wave is propagating. So we have wave propagation, and then we see that the elements of the medium are moving up and down. So we have simple harmonic motion of medium elements. And some of the things that we have to define here: highest point in the wave, so that's what I called point P here, is the crest. The lowest point minimum points is called trough. The distance between two consecutive crests, P to P distance, or Y to Y distance, or any other point that I take on the wave, and I look at the distance between consecutive same points on the sinusoidal, I will obtain one wavelength. All right, and On the other hand, if I sit at this point P and I watch how long it takes for the next crest to arrive, so I have an observer here, and this observer is basically measuring the time T0, the first crust has arrived, and then after a while at time T1 the second crest has arrived. So what this observer is measuring is the time interval between arrivals of two consecutive crests, and basically that will be one period. That's the period of the sinusoidal wave T. And on the other hand, if this observer, instead of measuring the time for the consecutive crests to arrive, measures how many crests we have in 1 second. So instead of doing this, I have 1 second and I measure number of crests arriving in 1 second. Then basically what I'm measuring is the frequency, the number of crests that pass point P in 1 second. That's what we call frequency. So the wavelength is measured in meters, period is in seconds, frequency is 1 over the period, it is 1 over second, or hertz, so what we call hertz. And how long does it take for this wave to propagate? Okay, so the number of crests that pass point P in 1 second is the frequency that's measured in hertz. On the other hand, I would like to know the propagation speed. So how long does it take for the wave to propagate one wavelength? So if you look at the arrival time between the time between the arrivals of two consecutive crests is 1 period. So if I measure the time for the arrival of two consecutive crests, basically I'm looking at a period. Therefore, the propagation speed that's V is going to be equal to the wavelength lambda divided by the period, or lambda times the frequency. So now I would like to obtain an expression for the wave function that describes this traveling sinusoidal wave. So how can I do this? First of all, if this wave is propagating to the right, as we have shown here, I know that the wave function has to have the following form: y of xt is equal to f of x minus vt. So if I apply this to a sinusoidal function, basically this should be of the form amplitude sine of a x minus vt. And now if I assume that at t is equal to 0, when I go to lambda over 2, so let's look at y as a function of x here. So this is lambda over lambda over 2. This is one wavelength. This is 3 lambda over 2. This is two wavelengths. And if I look at the wave function for a given point in space as a function of time, this is half a period, this is 1 period, this is 3t over 2, this is 2 periods. Alright, so basically I have for this wave function at time t is equal to 0, at position x equals lambda over 2, t equals to 0, I have a sine a lambda over 2. This must be equal to 0. So this a cannot be equal to 0. That means there is no wave. So the next value it can take, a lambda over 2, is equal to pi, or a is equal to 2 pi divided by lambda. Therefore, I find that the wave function y of x at t is equal to 0 is of the form a sine 2 pi over lambda x. Alright, and now if I rewrite my wave function y as a function of x and t, this is a sine 2 pi over lambda x minus vt for any arbitrary time t, and the wave function is traveling to the right. Then I have for v, that is one wavelength traveled in one period, so I can substitute this for v. I obtain y of xt is equal to a sine 2 pi over lambda x minus lambda times t over the period, which can be rewritten as y of xt equals to a sine 2 pi over lambda x minus 2 pi over period t. Or I can write it this way, a sine 2 pi parentheses x over lambda minus t over the period t. So that's one way of describing this wave function. It can be written this way. And just looking at what I have done right here, if I define 2 pi over lambda to be wave number, k 2 pi over lambda is defined as the wave number, and omega, which is 2 pi divided by the period, or 2 pi times the frequency, is defined as angular frequency. I noticed that with these definitions I have a new way of writing my sinusoidal traveling wave, so I can write it this way: y of x and t is equal to a sine kx minus omega t. So this is true if this wave is propagating to the right. And now there is the relationship between the propagation speed omega and k, the new introduced um, variables here. V is equal to omega divided by k. So omega is 2 pi over the period divided by k, 2 pi over lambda, lambda over 2 pi. That gives you lambda divided by the periods. So this is true. V is equal to omega divided by k. So there's one more task we need to consider. We have started out this discussion by saying I would like to have y of lambda over 2, 0 to be 0. So basically I had an initial condition here. I asked for this condition at lambda over 2. I want y to be 0. But in general I can have an initial phase. So y of 0, 0 does not need to be 0 always. So we can define an initial phase. In general, we can write y of xt is equal to a sine kx minus omega t plus phi for our sinusoidal traveling wave, which is traveling in the positive x direction. So the phase angle phi is the phase constant. It was 0 for the initial condition that I have considered, but in general this doesn't have to be 0. Now let's take a look at a specific example. A sinusoidal wave traveling in the positive x direction, traveling in positive x direction, has an amplitude of 15 centimeters, wavelength of 40 centimeters, frequency of 8 Hertz. The vertical position of an element of the medium at t is equal to 0, x equal to 0 is 15 centimeters. So I'm given an initial condition y of 0, 0 is equal to 15 centimeters, which is the amplitude. So it's the maximum. Find the wave number, period, angular frequency, and speed of the wave. Determine the phase constant and the wave function. Okay, so I start with the wave number. Wave number k is equal to 2 pi divided by the wavelength. Wavelength is 40 centimeters. So it is 2 pi divided by 40 10 to minus 2 meters. That's going to be 15.7 radians per meter. Then the period is 1 over the frequency, so it is 1 over 8 Hertz. So I find it to be 0.125 seconds. Next, angular frequency is 2 pi times the frequency, or 2 pi divided by the period, 2 pi times 8, so this will be 50.3 radians per second. The speed of the wave is its wavelength divided by its period, or lambda times the frequency. The wavelength is 40 centimeters, so I have 40 10 to minus 2 times 8. This is going to give me 3.2 meters per second. So from all of this information, I have obtained y of xt is equal to a sine kx minus omega t plus phi. That's the general form for a wave that's moving in the positive direction, a sinusoidal traveling wave. And the amplitude I have is given So I know the amplitude, I know k, I know omega. What I do not know is phi. So y of 0, 0 is equal to a sine phi. This has to be equal to a. So how is this possible? Sine phi has to be equal to 1. So phi should be pi over 2. Therefore, I can write the wave function, a general expression for the wave function. The general expression would be y of xt is equal to amplitude 15 centimeters, so it's 15 times sine kx 15.7 x minus 50.3 t plus pi over 2. And since I have included amplitude 15 in centimeters, this will be 15 multiplied by the sine function, giving me the position of the medium elements in centimeters, measured in centimeters with respect to their undisturbed positions.